Welcome to today's FDP session. Today is 25th April 2024. We have two sessions today. First session is on the topic of new physical and MAC layer paradigm for 6G by Professor Prabhat Kumar Sharma of Visvesvaraya National Institute of Technology, Nagpur, followed by session on 5G use case for various sectors by Sri A. Alex Vikas, ADG SRI and of DOT. Professor Prabhat Kumar Sharma is serving as Assistant Professor in the Department of Electronics and Communication Engineering at Visvesvaraya National Institute of Technology in Nagpur. With a robust academic background, he previously served as visiting researcher at the University of Southern California in the United States. Professor Sharma's research endeavor encompass cutting-edge domains such as molecular and biological communications, as well as the development of 6G and beyond wireless communication system. Recognized for his scholarly contribution, Professor Sharma has been honored with various prestigious accolades, including the Visvesvaraya Young Faculty Research Fellowship bestowed by the Ministry of Electronics and Information Technology, Government of India. In addition, he received the URSI Young Indian Radio Scientist Award in 2019 and was granted the SCRB SIRE Fellowship in 2023. Professor Sharma's commitment to advancing the field extends beyond his research pursuits. He actively contributes to the scholarly community through his service on the editorial board of esteemed journals such as IEEE Transactions on Communication, IEEE Transactions of Molecular, Biological, and Multiscale Communications, and IEEE Wireless Communication Letters. With this short bio, I invite Professor Prabhat Kumar Sharma to present his talk. We are eager to hear you, sir. Professor Sharma, over to you.
Thank you very much, sir, for giving me the opportunity to discuss my work once again. I would like to thank all the participants, Ashok sir and you, sir, for inviting me and inviting me again. Today, I will be talking on more about research things which are there expected in 6th generation of wireless communication systems. So I will be covering physical layer technologies, and then I will also try to cover the multiple access things which are going to be there in expected to be, or as a potential technology they are considered for 6G. Am I audible, sir? Is there an issue in my audio?
No issue, sir. You go ahead.
Sir, noise is coming, but voice is clear. Okay.
For you also, Sanjay sir?
I think some problem with the mic.
Yes, sir. For me also it is not clear. Audio is clear, but coming with some background noise.
Maybe your mic connection or the cable, sir.
Yeah, let me check. Is it better?
Yeah, better.
Yes, better.
Okay, sir. So whatever work I am going to present today, it is basically there are three parts. One is the.
So sorry for the interruption. Still the same status quo.
Okay, so let me remove my mic and then let me check. Just give me 1 minute then, sir. Am I audible, sir, now?
Yes, sir.
Is it better for others also?
Sir, your audio is okay, but the noise which is coming along with your audio is still there.
And sometimes signal is also cutting, sir. Your voice is maybe a
Breaking,
breaking.
breaking in nature.
Is it fine now? I don't have any mic or anything.
Yeah,
Sir,
this is fine.
Okay, sir. Okay, sir. So today, I hope I am audible and
Yes,
is no
better. Sir.
yeah. And if there is something, you kindly let me know. I will be talking about new physical and McLear paradigms for 6G. So basically, this topic would be covering three different topics. One is multiple access thing for sixth generation multiple access technologies. So I would be covering the background of introduction to uh, orthogonal multiple access technologies, then non-orthogonal multiple access technologies, NOMA, and then rate splitting multiple access RSMA. Then I would be talking about full duplex wireless communication. I think this topic has already been covered, so I would be touching a bit more about the research part, like mathematical modeling and those things, not in much rigorous mathematical details, but yeah, at introductory level. And then I would be covering a new kind of, interesting topic, which is a very interdisciplinary topic, and my colleagues from different backgrounds can relate to it. It is biological communication. I feel you will all find it different and interesting. So the slides, the work which I'm going to present today is done by many of my students and colleagues. So just would like to acknowledge them. Prasanna, Lokendra, Sivani, Sunil, Selma, Chandresh, Divyansu, Soumya, and Dr. Anamika. So they all have contributed to the slides content in some way or other. I work at VNIT Nagpur. So those who did not attend my earlier presentation, just an introduction. I work at VNIT Nagpur. This is one of the NITs situated in the heart of Nagpur city. We were established in 2000. It was established in 1960, but converted to VNIT NIT in 2000. This is our department. We offer BTech, MTech, PhD. You know, all our PG and UG courses are NBA accredited for full 6 years. We are the entire department is actively involved in R&D projects and consultancies. So this is our flagship conference. Some of you, those who are ready with some work, can think of submitting some of your work to this conference. It is PCEMS, and now we are going to host its third version in November 24. You can visit for more details the website of the conference. And then last talk which I gave in this FDP was on RIS. So based on the feedback received, and I received a couple of calls from the FDP participants and other colleagues. So we are planning to host one RIS workshop where we are thinking of providing hands-on kind of training to build, fabricate, and design RIS panels and how to use them in communication engineering. So this is still in ideation phase, and we are talking to different parties like IT. Probably Ashok sir also will take his guidance, and then Samir also, and we are planning to have it in June or July. So I will be in touch through our WhatsApp group about the updates regarding this workshop. So I have taken multiple images from internet while making this presentation. I do not claim any ownership or rights for those images. These rights lie with the individual creators or owners. This is just a disclaimer. So this is going to be the flow of my presentation. First, I would be covering multiple access in wireless systems. So evolution of different, generation-wise multiple access technologies, like what multiple access technologies we used in 5G, we used in 1G, then 2G, like that. And then I'll come to the rate splitting multiple access, RSMA. We'll cover it in detail, and then I'll move to other physical layer technology, which is expected to be, part of next generation wireless communication system. Although when I did my PhD, I worked on full duplex wireless systems, and that time it was 3G, so it was expected that full duplex will come somehow, some way in 5G, but it did not appear. Probably as a potential next generation technology, this field is still open. So I would be covering, specifically, I would be focusing on multi-user, full duplex scenarios where the how to model the self-interference and characterization of self-interference. Those kind of issues, topics I will touch, and then I'll move to the interesting topic of molecular and biological communication. So it is also expected that in the next generation, maybe 6G or 6.5 or 7G, there would be some interconnection of body area network, and like Internet of Things, it becomes Internet of everything. Then now it is becoming Internet of even nanobio things. So we will be having multiple sensors inside our body or any entity, living entity, and those sensors would be communicating with each other. So we are going to have a network inside human body, and it's not just the physical body. It may be there for different application like pollution monitoring, or it may be there for like water contamination in the supply water, and those kind of things, those kind of applications I would be discussing molecular communication for. So would first give you a brief introduction of molecular and biological communication, why it is so important for us to discuss it, and then how it is different from traditional communication, and then what are the transmitter receivers, and then bit of mathematical modeling, and what at VNIT we did contribute in this area. So this is going to be the overall flow of my presentation. So like United Nations, they have proposed, they proposed 17 Sustainable Development Goals, SDGs. So now these are the goals for next decade, to achieve it. These were proposed in the last decade, and for this decade up to 2030, we are expected to achieve these goals. So most of these goals now are like climate action or life on land, life below water. So we are kind of intermixing the digital technology with the biology or physical living things. So to achieve these goals, somehow technology should intervene, or it has already started in the going into the different biological or medical fields. Initially we were having just the medical equipments. Nowadays we are having in vivo all kind of technological advancements in medical and biological applications. So this is actually the necessity for not only for technology to move ahead, but also for the to achieve the better life on this planet. This technology should harmon should in a proper way, it should interact with biological world. Even I just read at some newspaper online, like United Nations, they think that we can't reach the sustainable development goals, we can't achieve without internet. So when they talk about life on water, life below water, or life on planet, we have to go for the ideas like Internet of nanobio things. So even people have started talking in their surveys and white papers, like there would be a biological layer for 6th generation wireless communication system. So with this in the background, I would be talking about biological communication. So I just would like to highlight one excerpt from one paper. This was published in 2020, that the future of connectivity is in the creation of digital twin worlds that are a true representation of physical and biological worlds at every spatial and time instant. and they will unify our experience across physical, biological, and digital worlds. So 1G to 3G, we mostly focused on speed and flexibility. It was more about voice connectivity. Then third generation and fourth generation, we shifted from voice to services and data, and mostly we were worried about data connectivity. We were focusing on data. And then in fifth generation of wireless communication, we moved towards more flexibility in terms of automation and industry. And we started, or wireless technology started catering to the business challenges. Now, in beyond 5G systems, in 6G systems, the focus would be on sustainability, achieving green communication, low power thing, then how to incorporate this wireless technology with medicines, Internet of Nanobio things, and then societal, societal, you know, how our technology is going to serve or provide better quality of service to the society. So this is going to be the kind of guidelines for sixth generation wireless communication system. So now setting this theme, like I just want to I just wanted to set the theme for my talk. So I would be covering three things. Two things are wireless, and one thing would be like related to biology, different thing. So I just shared with you the motivation. Why do we need to use wireless technology or in general communication technology for biological applications? So I would start my talk first with the multiple access technologies for next generation wireless communication system. So if you remember, uh, we have TDMA, FDMA, CDMA, and then OFDM, right? So all these multiple access technologies, these are orthogonal multiple access technologies. Orthogonal means if there are two users, right, they would be served by the base station or transmitter in orthogonal fashion. So the entire communication will exploit orthogonality either in time domain or frequency domain or port domain or in some other domain. There would be some orthogonality. What do we mean by orthogonality? Orthogonality means that signals of two users will not overlap with each other. So, for example, I want to talk to one of you, like, and or I want to talk to two of you. How can I do it? Either I can divide it in the time, like first I will talk to one of you and then other one. That kind of division is actually implying the orthogonality in time domain. So this kind of technology is called TDMA. And then we can have orthogonality in frequency domain also. Means for one user we can assign one frequency, and for other user we can assign other frequency. Two different frequencies can be assigned so that the signals cannot interfere. Signals are not going to interfere with each other. That is orthogonality in frequency domain. We can have orthogonality in code domain, like we did have in CDMA, code division multiple access, or like OFDM. So this, all these concepts we all know. So first generation of wireless communication systems, mostly they were focused. They focused on TDMA. They achieved the duplexity through TDMA, and then in second generation, things moved to frequency division multiple access, FDMA. Third generation, we were about CDMA, and now in fourth and fifth generations, we are using OFDM. The benefit or the advantage of orthogonal multiple access OMA technologies are that they are having very simple transmitter and receiver designs, and there is no interference between multiple users, or between any two users there is no interference, because you can distinguish their signals in some domain, like maybe in time domain or in frequency domain, so they can be perfectly separable, right? So there is no point of having interference in one user signal from other user. The issue with this is that the number of users are limited by the available resources. For example, like if you have 10 users and you want to divide you want to have a communication in time domain, TDMA, right? That fashion. So you have to, first user will be served in first slot, then it has to wait for 9 more slots, and again 11 slot would be its, right? So the rate of communication would be too slow, right? So as you will increase the number of users, there would be issues in each of these orthogonal multiple access technologies. Like in time, you will require more time. Like in frequency, you will require a large frequency band. Then here you will have to have a bigger code book, and then so the efficiency of OMA technologies, this is highly dependent on number of users, because you have to schedule them, right? Either in time or in frequency or in code domain. This is the disadvantage of orthogonal multiple access technologies. And with the with the advancement in the wireless technologies, now not only mobile users are increasing, but devices are also getting connected to the internet. So the number of users are actually increasing day by day. To cope up with this requirement, we have to move to a technology which is essentially not perfectly orthogonal, right? So we move to SDMA, where you can have same frequency, same time thing, but you are going to divide the user signal through some sort of beamforming. So for example, user 3, you will beamform in the direction of that particular user. User 2 signal, you will beamform in that direction. So what we are doing, we are multiplexing users in space domain, right? And how we are achieving the interference separation? We are achieving it through linear precoding. And still, if there is some interference, we will treat that interference coming to a user from other user as noise, right? So essentially, there was no interference in orthogonal multiple access. In SDMA, space division multiple access, we started dividing the resources in a space domain, right? But there is a possibility of interference, and while decoding a signal of its own, any user will treat the interference from other users as noise. So what do I mean to say is, for example, you have beamformed a signal like this, and signal of user 2 is beamformed here, but there will always be some leakage. You will also receive at user 3 some signal of user 2. So that would be an interfering signal, and it would be treated as noise while decoding the signal at user 3. So SDMA manages multi-user interference by spatial precoding at the transmitter, and it treats, just remember this, it treats the interference at receiver fully as noise, right? The advantage of this SDMA technology is it also has, not exactly like OMA, but it has again the simpler transmitter and receiver design. And this technology works well when the network is underloaded and you have the channel state information available at the transmitter. What do I mean by channel state information? Like if you want to beamform in this direction, so this beamforming performance will depend on the availability of this channel. If you know this channel in advance, you can beamform towards this user in a better way, right? So better are the estimates of the channel available to you. You can have better beamforming performance. Now in wireless, in real-time wireless situations, these estimates are tricky things. We cannot always have the good estimates of the signal. So this scheme SDMA is not going to is kind of it is challenging to achieve better performance when you do not have proper estimation of the channel or you have erroneous channel estimates. Then this scheme is also sensitive to network load and channel state information. How it is sensitive to network load? When you will have multiple users in a given area, this would be a dense network, and achieving the sharp beams is going to be difficult in RF frequency band. So it is a problematic issue, or it is it is a disadvantage of space division multiple access technology. So now from OMA to we move to SDMA. Now we are moving to non-orthogonal. It means we need not have orthogonality in some domain for transmitting the signal of two users. One example of NOMA is like power domain NOMA. What do we do in NOMA? We have in the same time, in the same frequency, we will transmit the signal of both users. Sorry, this is user 1 and user 2. So we will transmit the signals of both users, user 1 and user 2. But what we will do, we will divide or we will achieve the orthogonality in power domain, right? So some user signal, depending on again the statistics of its channel, we will allot more power, and some the other user signal will provide less power. Of course, the given total power is within the constraint of communication limit, which you can transmit in a given setup, right? Then when you are transmitting both signals in the same time, same frequency, they are differing in their power levels. How you are going to receive them at the receiver? So there is the idea of superposition coding at the transmitter. You will provide superposition coding here, and then you will do successive interference cancellation at the receiver. So, for example, here you transmitted signals with different power levels. So the combined signal, which is signal of user 1 and user 2, will be received by both the users, right? Now user 1, user 2, what it will do? User 2 will decode the signal considering user 2 will decode the signal considering the signal of sorry, let me just re-explain it. So both the signals will be received by both users. So user 2 will first fully decode the interference of which is coming from user 1 and will subtract that interference from the entire signal and will get its own signal. Then user 1, what it will do? It will do the SIC of user 2 signal, and then it will decode its own signal, right? So NOMA technologies, they manage multi-user interference by decoding interference at the receiver. In SDMA, interference was treated as noise. Interference was arising from other users, right? And here, decoding at a given user, you are not bothered about what the interference is. You just treat it as noise. However, in NOMA technologies, you have to treat the interference as a signal. You have to decode it, and then you have to subtract that decoded interference from your signal, and you will get your signal. Like that, you have to do successive iterations. So this successive interference cancellation means you have to decode the interference and cancel the interference. This technology is a complex thing, but it is coming with some gains. Like it provides you the non-orthogonality in time and frequency domains, right? So NOMA technology is also there in research domain since almost a decade or more than that. It was a study item for 5G, but it was not a work item in 5G. I believe that probably in 6G people will be discussing the NOMA technologies for incorporating it into the standards. The advantage of NOMA is it improves the spectral efficiency in overloaded networks, and the disadvantage is, like I told you, the complex successive interference cancellation method. So if there are issues or there is some this SIC, successive interference cancellation, is imperfect, then the performance of NOMA would be lower. Then you have more computational burden at the transmitter because transmitter has to do superposition coding. At the receiver, because it has to perform complex successive interference cancellation. And then this all is also vulnerable to the channel state information, because how much power you are going to allot to a particular user will depend on what is its channel. If its channel is good, you may allot it with lesser power. If channel is bad, you may allot it more power, or you may decide depending on your algorithm. But For allocating the powers to users, you need the channel estimates of the channel between base station and that user. So if we compare all these multiple access technologies, I am giving the case of say there are two users. So what we are doing in orthogonal multiple access technologies, we are scheduling one user at a time, or maybe some orthogonality we are achieving. So signal of one user only will be transmitted, maybe in frequency or in time or in other domain. In SDMA, what we are doing, we will be transmitting the signals of both users, but we will provide some linear precoding, right? And at the receiver, what we will do, because the signal of user one is beamform or focused on user one, it is going to mostly receive the signal of its own, but it may also receive the interference from other user. So that interference would be treated as noise, and the signal will be reconstructed at the receiver. In NOMA case, you have to provide superposition coding. So what you will be doing, you will be transmitting a combined signal, right, of all users. All users will receive the combined signal, and they will perform successive interference cancellation. And then, while performing successive interference cancellation, they have to decode the interference. Means they have to decode, any user has to decode the signal of other users, and then from the entire signal received, it has to remove that decoded signal to receive its own signal. So this is complex thing, but has to be done at the receiver in the NOMA technologies, right? So for two user case, I explained you we compare the performance, we compare the mechanism or the technologies of orthogonal multiple access, space division multiple access, and non-orthogonal multiple access technologies. I hope I'm clear. Is there any issue? My slides or voice?
Clear, sir. Except voice, other things are clear.
Okay, sir. Actually, I'm not using any mic also, so I don't know what is going wrong.
It's okay, audible, manageable. Yes, please proceed.
Okay, sir.
Then mostly your the speaker threshold point may be a different
Okay, ma'am.
system speaker point.
Yeah.
That may
If
be
it is
because
workable,
of
then
that.
we can continue, or I have to switch to some other system.
Yes, sir.
If you like. What do you suggest?
Sir, we can manage, sir. It's okay.
Okay, thank you. So the next generation wireless communication systems, as we know, they are going to provide Internet of Everything, higher throughputs, ultra reliability, then heterogeneous quality of service, massive connectivity, then localization, sensing, computing, and control. These all things are expected from 6th generation wireless communication system. Fundamental issue is when we are increasing the number of devices, we are talking about massive connectivity, and at the same time, we are also talking about ultra reliability. The issue with the increasing network density and massive connectivity is there is an increase in the level of interference. There is electromagnetic signal for each user, and we cannot have infinite frequency band to transmit. There are all the frequencies are number, but we can only use some finite frequencies for transmission. So resources are limited. In those resources, we have to cater to the requirements of too many devices, which are increasing day by day. It is going to increase the interference. So the most of the focus of multiple access technologies in next generation wireless communication system is going to be on interference management. How we are going to manage the interference. I'm just giving you a quick review. In OMA, there was no interference, so there was no issue of management. In SDMA, there was interference, but we were managing it by treating it as noise. In NOMA, there was interference, but we were managing it by doing successive interference cancellation, treating it as signal and decoding it out. All these things, they come with some cost. So we have to, most of the research in multiple access technologies have to focus on finding the novel ways in which you can increase the system performance without having much cost in terms of the complexity of the system operations and of course the money involved, right? So there are few methods suggested. One is at multiple access layer. People have suggested rate splitting multiple access technology, which is kind of combination of NOMA and SDMA, sort of. It is not combination, but it is kind of in one extreme it works as SDMA, in another extreme it works as NOMA. So it is a in between kind of technology which has the advantages of both. And then at physical layer we have I discussed in the last talk reconfigurable intelligent surfaces so that you can have more beamform signal at a desired location. I won't be talking about RIS today. I would cover rate splitting multiple access. And for those who are interested in RSMA protocol, understanding it, this is the good paper to read. It is by Professor Clarks from Imperial College London and his group. So how does RSMA work? Suppose you have two users. I'm going to explain it with the help of two users. There are two users. So the message of user 1 is W1 and message of user 2 is W2. What we will do, we will divide the user 1 message into two parts. One part is called common message, so the WC1. Other part is called private message, WP1. Okay. Same way we will divide the message of user 2 again into two parts, the common message of user 2 and the private message of user 2. So essentially, if there are multiple users, we are dividing the message of each user into common part and a private part. Now we will take all common parts together, WC1, WC2, and if there are more users, WC3, WC4, all we will take together and we will merge them to make a combined message, WC. So WC is a combined message, okay, common message, which is common for all, which is common for now all users, right? Because it includes common part of each user. Okay. Then what we will do, we will we will encode the common part of the global common part into one signal, say SC, and individual private parts we will encode separately. So all this encoding will happen independently. Means SC is independent of S1, like that. Then what we will do, then we have to transmit the signal. So transmitted signal would be the linear combination of or some beamform version of a common message SC, right? Which would be multiplied with a weight, say PC vector, and then there would be message S1 multiplied with P1 and S2 multiplied with P2. So this way, this combined message we will be transmitting. I am explaining it again if you didn't understand. We have a message, we'll divide it into two parts, WC1, WP1, right? Same way we will divide the messages of all users, and we will collect all the common messages into one bunch, and then we'll call it a global common message. That global common message will be encoded independently, and all other private messages, WP1, WP2, WP3, all will be encoded independently, separately, right? And then we will combine. Of course, we can provide some weights, some precoding we can do, and then we can combine, we can transmit the combined signal, which will be PC vector SC plus P1 vector S1 plus P2 vector S2, right? I hope this is clear. If there is any issue, I can try explain it again. Now at the receiver side, so at the from the transmitter side, we are transmitting this. At the receiver side, what we will do, we will first try to decode the common stream SC, right? So we will decode the common stream. While decoding the common stream, we will treat S1 and S2 part as noise. This is similar to what we were doing in SDMA, right? In SDMA, while decoding the desired message, we were considering the interferences as noise. The same thing we will do. We will first decode SC, right? We will first decode SC by treating S1 and S2 as noise. Then what we will do, once SC is decoded, then we will subtract that SC, and from the remaining messages, we will perform the successive interference cancellation. And then, like in NOMA, we will decode S1 and S2 on the same way like we did in NOMA. So in some part of the message, we are doing what we have done in SDMA. In other part of the messages, we are doing what we have done in NOMA. So by controlling the amount of messages, amount of bits, or amount of length of message in WC and WP, we can actually control that how much message we want to be decoded as SDMA and how much message we want to be decoded as NOMA, right? So controlling the length of message means controlling the rate of the message. We can determine how we are going to decode it. So we are splitting essentially the message in rate or in terms of its length of the message bits, right? So we are essentially dividing the messages which are to be decoded by treating noise, by treating interference as noise, or by decoding interference fully and doing SIC. So we are doing this by splitting the entire message in the rate domain, right? So overall rate is split into two parts. One is the rate of kth user, and other is the rate of common message. Is this clear, or is there any question on this?
So what is the condition to have WC or WP? What is the logic with which we can divide the particular message?
Yes, sir. So like there is, suppose there are two users and the message is of 10 bits. So what you can do, for first user, you can divide, say 3 bits are common and 7 bits are private. So 3 bits, when you are saying common, you will be decoding those 3 bits as SDMA.
No, my question is on what basis I can choose 3 bits for common? It could be more than 3 or less than 3.
Yeah, that will depend on how much performance like you want, sir. So for example, there is a factor, we call it alpha C, right? So alpha C times alpha C fraction of the message you provide for common, and then 1 minus alpha C you provide for private. Actually, it depends on many things, sir.
Is it function of decoding?
Is it the function of
decoding mechanism?
No, not precoding, sir. This is
precoding. Is it function of decoding logic?
Yeah, it is function of decoding logic. It will determine the decoding also.
Okay, got it.
And how much portion you are going to give for, say, alpha C and alpha P, it depends on number of users also. Like for example, if there are 100 users and for each user you have taken 3 bits as common, so there would be 300 bits, right? So that common message would be too long. So actually it depends on so many factors, sir. We have publication in that direction where we have tried to find out the optimal alpha C, the rate splitting factor. I did not include it in the presentation, but I can direct you to that paper maybe. But yeah, it depends on the number of users in the network and of course the channel statistics of those users.
Thank you, sir. Thank you.
Okay, so this was the new technology. I did not, include the results related to it. I just to cover more of biological communication thing, because I feel that would be a more interesting topic for the audience. If anyone has any doubt or any question on RSMA, I would be happy to answer. Please go through this paper, rate splitting for MIMO wireless networks. It is a good read, kind of theory read, and then even our group also has couple of papers on rate splitting and RIS combined together in TWC TCOM. So I can provide the links in WhatsApp group. Then I would go like this is kind of general thing. I would just cover the full duplex communication. So essence of this full duplex technology is, I'm just talking about it because it is one of the potential technology for 6G communication. I hope this topic has been covered, but just in a couple of minutes would like to give you the idea how it is different from the conventional duplex. So when we teach in classes or like our communication, like I was speaking and sir was asking the question, right? Or we were having a discussion. Was it not full duplex? So we define the duplex in terms of the bidirectional communication. If the communication can happen from one side to other side only, it is simplex. Then it can happen from both sides, but one at a time, it is half duplex. And then if I can also speak, you can also speak same time, both ways, it is full duplex, right? This is the notion of duplexity in our, especially this is what we teach in our classes, right? This duplexity is, however, different from the traditional duplexing mechanism. Like you were achieving bidirectional communication, either in time domain, you are dividing the resources of time or frequency. Like when me and sir was discussing the RSMA question, it was basically the division in frequency. There was an uplink frequency and there was a downlink frequency. So we divided the message in frequency domain, but we could talk in the same time. Similarly, you can talk in same frequency, same frequency signal, but in different times, right? So this was duplexing. We were achieving full duplex through this duplexing. Now the idea of this present full duplex wireless technology is we were not having orthogonality in time domain or in frequency domain. It would be one antenna, same time, same frequency, and then achieving both directional communication. This is going to be, this is what the people are talking for, full duplex communication in for next generation wireless communication methods. Like these things, I believe, are these things have been covered. So this is going to happen like this. Suppose this is the FD node, full duplex node. It has say two antennas, transmitter and receiver. This guy is transmitting a message to this guy. The message is hello, how are you? So first time instant, it is sending hello, right? Next time instant, it is sorry, message was hello Jack, not how are you. So first time instant, it is sending hello. Second time instant, it is sending Jack. And when it is sending Jack to this guy, this FD node is transmitting hello to the other, forwarding the hello to other guy, right? So what will happen in the second time slot when this FD node is transmitting to this person, the transmitted signal will also be received by its own receiver, right? So this signal hello is going to come back again to the to the receive antenna, from where it is going to receive Jack. So now Jack and hello would be interfering with each other. Just a basic antenna principle, because this is a single node and this signal is coming from a far device. What will happen? This signal, which is desired, means Jack signal, it would be a weaker signal because it has been attenuated over the distance, right? However, this signal, because it is coming from the same device, same node, it would be strong, and there would be a huge power differential between the desired signal and interference signal. So interference signal is going to dominate the desired signal. This interfering signal is called self-interference or residual self-interference, or in some way, in some text, it is also mentioned as echo interference, because this is an echo of Echo means we listen to what we are transmitting. So this technology is a potential technology, specifically the hardware implementation. People may ask, like, has it been implemented? Yes, for Wi-Fi devices and those. A rigorous, huge research has been done in this area, and people have come up with active interference cancellation, passive interference cancellation, all those cancellation technology people have invented, and this uh, full duplex technology has been implemented in real sense, right? For the research purposes, like how to characterize this RSI, for analyzing the performance in those, there are two methods. One method is you can treat RSI as constant interfering power, and you can have it as the denominator of signal to interference and noise ratio. So you can just add the power of the signal, power of the interference into the power of noise, right? Other ways, you can have a random approach. You can assume that the signal which is coming from your own transmit antenna, you can model it as random signal, and then you can use the probabilistic approach to evaluate the performance of this kind of systems. The experimental results, they concluded that the modeling for modeling of self-interference signal, the Bayesian distribution with lower value of parameter k is a best fit. So mostly people were modeling the self-interference as constant power, but this approach is not correct. They have to, while designing the system, while evaluating the performance of system, they have to model it as a random variable, specifically the Bayesian distributed random variable. Why Bayesian? Because this is going to be mostly on LOS, and there would be lesser multipath components. But because you are applying cancellation technique and separation techniques, you can have lower value of K factor for this Bayesian, right? So our group, we have done a lot of work on full duplex wireless communication systems. So this is one of the technologies for 6G, and there is a lot of scope still for people like us to work in this direction, specifically the hardware implementation of these systems. So maybe we can consider, for IP creation and those things, because this technology is, I believe that it's going to be part of 6G. Maybe a bit later it is going to come, but as under the umbrella of 5G labs, we are planning to get prepared for 6G IP creation and those things. So we may put our efforts into this direction of actual implementation of full duplex systems. The research may go in like antennas, the RF, signal processing, all these kind of domains we can work on it. Now I'm coming to the other interesting topic of my talk, which is molecular and biological communication. So we know that in nature, communication happens even at nanoscale level. For example, if you are walking and if there is an insect coming towards you, your eye will blink by itself, right? You need not provide an attention to it, and it will do its job. Why it is happening? Because there are senses. You have the sensors. Our body, nature has given us those kind of abilities so that we can sense, we can act on those sensing, and we can react also, right? So same way, even the blood cells, even the tissues, the animal cells, they communicate with each other for different needs, for the need of energy, for the need of so many other functions. They communicate with each other. Communication happens between blood cells, communication happens between community of cells, communication happens between a colony of bacteria. So at this level, communication happens. This communication, again, when there is a communication, there is a transmitter, there is a receiver, there is some media, and then there is some kind of information carrying entities, right? All these things are there. This communication essentially is similar to what we have in wireless communication or normally digital communication system. However, this is not kind of Wi-Fi or uh, uh, Mbps rate kind of communication. This communication happens at very small scale, at nanometer level scale, and the rate of communication is also very less, right? So although they are similar kind of systems, but they are not similar. They are not similar in terms of the scale, right? In I have a slide for the comparison of this. So molecular communication or biological communication is the field of communication engineering, which involves the background from biology, which involves the background from physics, background from materials, chemistry, mathematics, biotechnology, electronics engineering, of course, wireless communication. This is an interdisciplinary area which is in focus to target to understand the existing communication mechanism within the nature. Nature has provided us the abilities to communicate. Even the small cell can communicate with other cell. To understand that method, to understand how one cell communicate with other, and to mimic that. So just you would be surprised to know that people have started mimicking the nano communication system, means this molecular communication systems they've started implementing, and they've started implementing the nano robots which can go inside your body and can communicate with each other, can travel at some distances, you can localize them, all such kind of things. These are not just theory, they are actually implemented. These systems are actually implemented at a couple of places. Now the idea is there is a lot of scope in this area where the doctors, people from medical field, material field, we can come up together and we can actually contribute to this big area which is called Internet of Nanobio Things, by first understanding how different communication mechanism happens and then mimicking the systems exactly what nature is doing for us since ages. So these are like the example of communication, like quorum sensing, right? Quorum sensing is one of the example of molecular communication system. Bacterial communication is other example, like all the bacteria can communicate with each other, where to go, right? How to respond to changing environmental conditions. All these bacteria, they communicate with each other. So what is the importance of this molecular communication, where we can apply? We can apply molecular communication systems where electromagnetic waves cannot serve the purpose. For example, wireless communication system, we use mostly the electromagnetic wave for carrying our message from one place to other place. But inside the tunnels, we find it difficult to have wireless connectivity. We can use molecular communication there. Inside gas or water pipelines, we can have molecular communication, right? We can have molecular communication inside the buildings structures, like inside the concrete things, we can have molecular communication. Inside our body, we can have molecular communication. We can use molecular communication for diagnosis. We can use molecular communication for targeted drug delivery systems. All these things, the molecular communication actually can help it. Molecular communication, they do not suffer with the disadvantages of electromagnetic signals. Whatever electromagnetic signals, like they attenuate with distance and those things, they do not suffer the same way, but they have their own challenges. I would explain in more details how information is carried from one place to other place and what are the drawbacks or limitations of these kind of systems. So if we compare, before going ahead, if we compare molecular and traditional communication systems, like devices in telecommunication system, they are mostly electronic devices, and in molecular communication systems, these are bio-nanomachines, right? They are nanoscales, their dimensions are nanometers, and mostly they are biodegradable, biologically degradable devices. The signals in telecommunication, they are optical or electrical signals we use, while in molecular communication, mostly we use chemical signals. The information that we exchange is digital. Here we exchange physical information or chemical information. The speed of propagation or the speed of communication is, in case of telecom, it is that the speed of light, whereas in case of molecular communication, we just have very slow speed, right, in micrometers, like that. Energy requirements, here we use electrical energy or electromagnetic energy, and requirements are very high, whereas in molecular communication we just need chemicals for transmitting the information from one place to other place, and the requirements are low, right? With the advantages, with the journey from one generation to first generation to sixth or fifth generation, we have become lot of precise and accurate in telecommunication systems, whereas molecular communication systems, they are in their nascent stage, they are just in their beginning, and we are yet to achieve that kind of stability and accuracy in molecular communication systems. So the simplest type of molecular communication system is a diffusion-based molecular communication system. What do I mean by diffusion? For example, this is the source of the communication. Suppose this guy is sneezing, right? So it is releasing the air drops, water drops in the air, and the gradient of air drops is more at the location of the receiver, right? And then these air drops, water drops, actually moves in the air. They started diffusing in the air and reached to the receiver. That is how the disease is spread, right? So same mechanism. This is the mechanism of molecular communication. So you have a high gradient, high concentration of molecules at a location, and those molecules, because of law of physics, they will start diffusing in a direction of lower concentration gradient, and that diffusion will take place. And of course, it depends on the speed, it depends on the diffusivity of the media, but it will not take place at the rate wireless communication is taking place, right? So essentially, the diffusion-based molecular communication systems are the simplest communication systems, and we can find them, at many places in our real life. So we have a transmitting nanomachine. Transmitter we call transmitting nanomachine. Receiver we call receiving nanomachine. Then there are messenger molecules. Then we do all sort of encoding, decoding. Propagation happens. Sending, receiving we do. Then there are information molecules, addressing molecules, interface molecules, all these kind of things which are there in normal digital communications, conventional digital communication system. They are also there in molecular communication system. For example, this guy, this is a transmitting nanomachine or transmitter. It will generate the information carrying particles or molecules. These particles will propagate. Now propagation can happen through diffusion, means there is more concentration of these particles here, so they will diffuse towards the low concentration. This is the ideal diffusion. You can have drift, means this guy can provide some force, it can release, like we do in sneezing, like this guy can provide some force, and along with diffusion, the particles will move towards the receiver. Or there can be so there can be diffusion, there can be drift, and there can be drift and diffusion both, right? So this would be the channel, the media would be the channel. In case of normal, air is only the channel, while in case of our inside body, the blood vessels are the channel, right? And then you have a receiver nanomachine, which will have a transmitter. It will absorb the molecules, information molecules in the environment. From the environment, it will absorb and it will provide it to the decoder, and those molecules would be decoded in some fashion by the receiver, right? And the information would be extracted. So transmitter encodes the message onto the molecules instead of electromagnetic wave. Now the message would be encoded into the molecules, right? Molecules, they propagate in the media either by drift or by diffusion or by both. Then they reaches to these molecules reach to the to the receiver. Receiver, depending on its nature, can absorb them, and then it can start the detection and decoding of the message from this received molecules. Okay, so yeah, this I have already explained. Yeah, so they are the example of our real life nanomachines like endocrine hormones, right? These are used as the messenger molecules by nature in our body. We have cytokines, we have neurotransmitters, intercellular messengers, even DNA, RNA molecules. They are also used as messenger molecules. And the media, it can be, like I told, pure diffusive or advection assisted diffusive. Advection is drift assisted diffusive media. We can have 3D channel, we can have 1D channel, all such kind of, for example, like your blood vessel, right? Its cross section is very small compared to its length, so you can assume it as 1D channel, right? It is a cylindrical channel. It has blood velocity as well as diffusion, so it is advection plus diffusion, advection assisted diffusion channel, right? This is the example of channel. Now, what kind of molecules you can use for carrying the information? It depends on which media and what applications you are using. Yeah, we can decode the message depending on, the simplest thing is based on the concentration. So you can decide the time slot like T1, T2, T. In 1T, you will find out, you will transmit some molecules for continuous T duration, and then receive at the receiver side, you will receive for T duration, and you will check how many number of molecules are being received. Then you will compare that number of molecules to be received with a threshold. If the number of molecules received are above threshold, you will say that symbol 1 was or bit 1 was transmitted. If the number of molecules received are lesser than what the threshold you decided, then you will say that bit 0 was transmitted. So this is the simplest way of decoding the information. Right, then you have different types of other molecules like interface molecules. Interface molecules, they allow transmitting nanomachines to transport the variety of information carrying molecules using the same communication mechanism, right? They allow any type of molecule to be delivered to the concentrated, and concentrated at a target location. Then you can also have addressing molecules, which are used to provide you the address of given TN, transmitting nanomachine or receiving nanomachine. At the receiver end, you can have active receiver, passive receiver, or reactive receiver. So active receiver is one. It will receive the molecules only when the molecules collide to the surface of the receiver. So wherever the molecules are diffusing, molecules are propagating in the environment. So whenever the molecule, information carrying molecule, will touch on the surface of this active receiver, the receiver will absorb them, right? Then there are passive receivers. What passive receivers will do, they will just count the information. So number of molecules will pass through them, and they will just count the number of molecules which have been passing through. They will not absorb them. They will not. So these molecules will remain further in the channel, right? So this is the passive receiver. In active receiver, once the molecule is touching the surface of the receiver, it is gone, right? Of course, it would be used for decoding, but it will not further be allowed to come again out of the receiver, right? Whereas in the passive receivers, molecules can come out of passive receivers. Then there are reactive receivers. So reactive receivers, they have these kind of spikes. These are called proteins, receptor proteins. So these receivers, these proteins, they try to catch the molecules from the, so the surface is having the spikes, these proteins, and these proteins will react or will catch a specific type of molecules which are kind of destined to these proteins, and only the molecules which are compatible with these proteins will be received and decoded. So this kind of receiver is called reactive receiver. We call it partially active because not the entire surface, but only the surface where the proteins are there. These are used as the receiver, right? Not the entire surface. Now, diffusion phenomena we all know. I will not discuss it in the detail. There is a greater concentration here. Then after some time, the concentration, the molecules will diffuse inside the entire space, right? How do we model the diffusion? So we assume like a location of a given nanomachine or molecule at a given say spatial coordinate, and then we will all these three axes x, y, z, we will model as the displacement in all three axes. We model as the Gaussian distributed random variable. So, for example, the current coordinates are x, y, z. After delta t time, the coordinates would be x plus delta x, x plus delta y, x plus delta z. So this delta x, delta y, delta z, which is the shift in space, will be modeled as Gaussian random variable. This is the principle of diffusion and Brownian motion. And the diffusivity of media can be defined using the Boltzmann constant, temperature, and radius of the particle using this formula. Then there are different laws which play important role in defining or understanding the molecular communication. Fick's law, where first law and second law. So Fick's these laws, they are the differential equations which provide you the relation between concentration at a given location and given time and other location and other time, right? So you can solve these differential equation under your given scenario. You can have the initial conditions based on the system model you are taking, and then you can solve the differential equations in the given setup and can reach up to the then you can find out the number of molecules being received at the receiver, right? Of course, you have to consider all the initial conditions and other things. And for reactions, you can use the chemistry, related principles, and then, so for example, you can use for information carrying molecules, you can use some chemicals, and those chemicals may react to the proteins, right? And can become altogether a different element. For example, hydrogen, oxygen combined in a given proportion makes water, right? Same way, you can have the transmitter and receiver which work on the chemical reaction principle. I'm not going into much details, but if you have some questions or queries, I would be happy to answer. So all these are chemical reactions like first order, second order. So all like while modeling the system model, you can consider all these aspects. So I told you, like, you can assume an initial location, then you can assume unbounded three-dimensional space. To start with, you can have just diffusion, and there is no advection in the system. You assume that at the time t equal to 0, some impulse of molecules is released by the transmitter. Then this is the Fick's second law. You can solve this. Differential equation to obtain the concentration C at a given d and t, and this is found to be the solution is this. So this is a standard thing, right? Only thing is, while solving this differential equation, you have to take care of the biological aspects and physical aspects of a communication system. Then, like I told you that in electromagnetic signals, signal goes down or attenuates with distance. Same thing happens with the molecular communication system. So number of molecule going to be received as a receiver, this number decreases with time because either the molecules will pass the location of the receiver, or they are too slow to be received. So means the diffusion, they have the lesser diffusion coefficient. So they would be received. There would be a peak time when most of the molecules would be received, and then this time will keep on, the number of molecules will keep on decreasing with time. While for this example, we did not consider any advection, we just consider only the diffusion. For considering the advection, you can consider the different other factors, like this V factor will come for velocity, and this is for chemical reaction, right? So when you have only diffusion, you can use this part of the equation. When you have diffusion plus advection, you have to use this, and diffusion, advection, and chemical reaction, then you have to use the entire thing. So when you make this system model, complex, of course, the mathematical and analytical treatment of the subject become complex. But yes, there are nowadays simulation softwares. People are doing particle-based simulation, Monte Carlo simulations, and their advancement in mathematical techniques, specifically the numerical methods. So we are able to find out, the behavior of biological, or we are able to study these kind of systems in detail. Okay, so now I would like to tell you what we have done at VNIT. We actually implemented a benchtop molecular communication system a couple of years back, and we are working on its improved design. What we did, we took normal, cold drink bottles, and we made electronic spray. This spray was controlled by a microcontroller. This microcontroller was connected to the computer, laptop, through which we are sending the message. And now we filled this bottle with isopropyl alcohol, and corresponding detector we used at the receiver. So we used simple on-off key for some particular time duration. We say for transmitting 1, we turn on the spray, and for 0, we did not, we kept the spray off, right? We did not transmit anything. So at the receiver, when there was some spray, some concentration of the isopropyl alcohol was received and detected by this sensor. So we could find out like whether 1 was transmitted by the transmitter or 0 was transmitted by the transmitter. The problem was the spray, when the isopropyl alcohol was falling on the surface of this sensor, it was taking a bit more time to, for the surface to get clean. So when there is some concentration, the sensor was reading the higher value of concentration, even when you are not transmitting anything, but it was giving you a positive reading, like 1 is transmitted. So that issue we had to solve, and we could solve it by proper synchronization, by providing proper time instant for 0 and 1 transmissions, and we could do it. Using this principle, we could implement like 4x4 MIMO system, molecular communication MIMO system, and we were able to achieve the transmission from this side and this side. This is just a photo. We did it for different settings, like we provided a fan behind it so that there is some drift also. We changed the distances, all sort of combinations we did, and we are now improving the system for specifically the synchronization part. We are now improving to have more more speed of communication. In this thing, we could achieve 0.7 bit per second, right? In this scheme of thing, with single antenna, single molecular transmitter, and single molecular receiver thing, we could achieve 0.7 bit per second. Apart from this theoretical studies and this practical test bench setup, we are also designing the biosensors which are based on photonic integrated circuits. So what we do, we try to say for different diseases like cancer and those diseases, we are trying to implement the biosensors which can detect the disease as well as it can communicate to the other sensor or other node. It can transmit some information, yeah, that this is the location of the disease, or I found that disease. The principle of this biosensor is we are making it using silicon photonics technology. So the principle is when it will emit some light, and depending on the refractive index of the light it is receiving back, it will determine whether the light is coming from the cell or it is coming from a malignant cell. So we could implement this for cancer, and now we are extending this work to different diseases, and then how to incorporate these sensors in the transmitter and receiver section so that we can demonstrate it. The actual nano dimension biosensor based molecular communication system. So for future scope of molecular communication system, we can use it for environmental monitoring. Like in industrial area, you can have sensing of the environment, and then those sensing molecules only can communicate the status of particular gas, say nitrogen or carbon dioxide, to other locations. It can help you control the waste, pollution, those things. You can have large-scale healthcare systems. You can use the molecular communication there. And then for targeted drug delivery, treatment, nanosurgery, you can have robots. Recently, one of my friends visited, one German conference. It was on medical sciences. So they demonstrated that a nano robot carried a male sperm to a female egg. The male sperm was carried by a nano robot to a female egg. So that robot was capable of sensing the sperm, finding the way to the egg, and delivering the sperm at the female egg, and it actually resulted in proper pregnancy. So these kind of systems are actually coming up. In our country, I think not many groups are working in this area, but this is highly interdisciplinary area where we can actually start working and can can create a lot of IPs for the system. Those who are interested in learning this molecular communication system, IEEE has started a society. IEEE's Communication Society has started a technical committee, molecular, biological, and multi-scale communication. I'm the social media chair of that committee. We have a YouTube channel where speakers from all over the world, those who are working in this area, I upload their videos time to time. So this is good educational resource. We have a LinkedIn profile. We have Twitter presence, and you can reach to us through this Gmail ID also if you need any help. And then there are good resources on molecular communication in IEEE and other databases. So like we at VNIT we work in the areas of wireless communication, RISs we are working nowadays. We are working on biosensors. We are working on molecular communication systems. So would be happy to discuss and collaborate if some of you wants to discuss these things with me. Thanks a lot for your attention. If there are questions, I am open.
Good morning, sir. First of all,
Yep.
I'll thank and for wonderful session. It was really, we can think about the application in healthcare. Okay.
Yes,
So,
thank you. Actually, we
my
have many medical or health related university also got 5G lab, right? So although this biological thing is not part of 5G, but yeah, they can contribute to IP creation in 6G system for 6G systems. Yes, ma'am.
Okay.
Please.
Yeah, I'm from University of Hyderabad, Computer Science Department. So we do have a life science department because
Yes,
your
ma'am.
lecture is making us to think in this direction. Uh, Here, sir, one my question. So, as a cell community, the micro cell communication, you are thinking. So, if really it works, thinking on these directions, so we can think about how the simulation of these things work out, and so that the cancer cell, the communication, and how fast it is growing and slowing down kind of thing. Is it possible to think in this direction for other than biology people?
Yeah, sure. Actually, not other than, but along with them, we have to like as a
Along with
computer
them.
scientist, man, you can actually come up with the AI models also. Like AI can play a huge role. If you
Yes,
go
sir.
and check the papers in this area now, molecular communication committee or biology community, they are started incorporating AI for prediction of cancer and those things, right? So
Right.
I totally agree with you, ma'am. Like by observing the communication pattern, we can, and then predicting it for the future, we can actually come close to the prediction of cancer. I believe this.
Mhm. Thank you, sir. Because it's a very new direction.
Yes, ma'am.
Still, we
And
need to go
actually,
through that thing, and then only we can able to ask you the questions. Because your session was really wonderful, sir. Thank you.
thank you, ma'am.
May I
Is
ask
there any other?
all others participants also to open your video and mic for a moment and then ask your questions. In the meantime, Prabhatji, if you can unshare your screen.
Yes, sure, sir.
Yeah, thank you. Thank you. So any more question for Prabhatji? Okay. So, okay, if there is no more question, then Madhukar, please offer a formal vote of thanks to Prabhatji.
Yes, sir. So, on behalf of the BP team and all participants, we express our heartfelt appreciation and gratitude to Professor Prabhat Kumar Sharma for agreeing to our request to take another session. This has been his second session in this FDP program. Thanks for that, and to your team members who also contributed for this session. Sir, your presentation was both informative and engaging, provided valuable insights that shows the path forward in this emerging field. Professor Sharma's passion for his expertise and his commitment to share the knowledge will serve as an inspiration to strive for excellence in our field. Dr. Sharma's contribution as a distinguished speaker has greatly enriched our faculty development program and added as the diverse content in the overall faculty development program. We also extend sincere thanks to our enthusiastic participants whose valuable contribution and time investment has made this event fruitful and successful. Once again, I thank Professor Prabhat Kumar Sharma and his team and all participants. All gratitude to all involved. Warm regards. Thank all of you. All regards. Jai Hind, sir.
Thank you, Madhukar. I think our new speaker has already joined. I can see him. Alex is there. I think he's on phone also. So Alex, good morning, Alex.
Sir, very good morning.